Hello, I'm Sarita, and in this lecture we will be discussing about the interior of stars. We know that most stars lie on a band in a HR diagram which runs diagonally across this. Sun also lies in this band which belongs to the main sequence star phase. This diagram shows the HR diagram of a few stars. One can see that most stars run diagonally from the top left to the bottom right. The stars on the bottom right represent those which have lower surface temperatures and have lower masses. The ones on the top left are those which have higher effective temperature and higher masses. In order to understand why most of the stars lie on the main sequence band, it is important to understand the processes in the interior. First, let us try to understand what is the source of Sun's energy. Is it chemical energy? Is it gravitational potential energy? Or could it be due to nuclear processes? In order to get an estimate, we provide important constraints in the form of the size of the Sun, mass of the Sun, luminosity, and age estimates, which can be obtained from radioactive dating of meteorites. Let us first consider the case of thermal energy. During the collapse of a star, it gets heated and gravitational potential energy of the star is converted to thermal energy. Now, if we assume that this thermal energy is radiated from the Sun at a constant rate equivalent to the luminosity, then it is possible to estimate the lifetime of the Sun based on this energy scale. So, if the thermal energy is of the order of magnitude of the gravitational potential energy, then this is equivalent to gm square by r, where m is the mass of the star and r is the radius of the star. Once we put in the values of the mass of Sun and radius of the Sun, we get the lifetime as nearly 10 million years. We know that this is much smaller than the age of the solar system, which has been estimated by various different techniques, such as the age of rocks on the moon and the dating of meteorites, and it has been found to be 4.6 billion years. The timescale calculated in this way is known as the thermal timescale or the Kelvin-Helmholtz timescale. So, it is obvious that thermal energy cannot be a source of the Sun's energy. We next try to understand whether nuclear processes can lead to the source of Sun's energy. For this, we assume that the Sun is fully composed of hydrogen, and we consider the case of the simplest fusion reaction, that is the fusion of protons to a helium nucleus. From laboratory experiments, we know that the production of each helium nucleus releases an energy which is 0.7% of the mass of the reactants. If we assume that nearly 10% of the Sun's mass at the core, where the temperature and pressure is maximum, undergoes nuclear processes for the release of the energy, then during the entire lifetime of the Sun, the core will be converted to helium. The lifetime can be estimated by calculating the energy released during the nuclear fusion processes and dividing it by the rate at which it is radiated out, which is the luminosity. And the energy radiated during the nuclear fusion processes is given as 10% times the mass of the Sun converted to energy, that is equal to mc square, and we also consider the efficiency, that is 0.007. This gives us a nuclear time scale of nearly 10 billion years. This is of the order of magnitude of the age of solar system, and therefore one can safely presume that nuclear energy is the source of Sun's energy. So, this time scale is known as the nuclear time scale. During the lifetime of a star, there are 3 time scales that are important. Of these, we have already discussed 2 of them. One is the nuclear time scale, the other is the thermal or Kelvin-Helmholtz time scale, and the third time scale is known as the dynamical or free fall time scale. This time scale corresponds to the total time scale for the collapse of a star to a point under free fall conditions. This can be calculated by taking a ratio of the size of the star to the characteristic velocity in gravitational field that corresponds to the escape velocity. And this dynamical time scale is found to be inversely proportional to the square root of the mass density. If one compares all the three lifetimes, then one finds that the dynamical time scale is much smaller than the Kelvin-Helmholtz time scale, which in turn is much smaller than the nuclear time scale. Now, let us try to understand the other processes in the main sequence phase of the star. First, let us consider the size of the star. We know that the size of the sun does not change with time. This means that the gravity forces in the interior of the sun are balanced by other forces. What could these forces be? These forces could be due to thermal pressure, due to radiation pressure, or any other form of pressure. This implies that there is an equilibrium between the gravity and other forces. This equilibrium is known as hydrostatic equilibrium. Let us try to derive a relation for the hydrostatic equilibrium. For this, let us consider a sphere which we take to be the star of radius r. We consider a small cylindrical volume element at a distance of small r from the center. The mass interior to the shell is given by mr. The mass of the cylinder is given by dm cylinder. The cylindrical volume element is shown on the left side. One can see that the plane surfaces of the cylinder have an area dA. The height of the cylinder is dr, corresponding to the shell within which it is embedded, and the mass of the cylindrical volume element is given by the volume of the cylinder multiplied with the mass density. We assume that the mass density is not changing significantly across the shell of thickness dr. Now, the gravitational force between the cylindrical volume element and the mass interior to it is given by this relation dFg is equal to minus g, the mass interior to the shell, the mass of the cylindrical volume element, by r square. This is equal to minus g m of r rho by r square dA times dr. Now, if we consider the other pressure forces, then due to the pressure gradient between the top and bottom of the cylindrical surfaces, this is given by this expression here. Note that only the forces due to pressure on the plane surfaces are considered. This is because the other forces on the curved surface at the same radial distance balance and cancel out. Therefore, the force due to the pressure gradient is given by dFb is equal to minus dP dA. Here the radial direction from the center outwards is taken to be the positive direction. Under condition of hydrostatic equilibrium, these two forces balance out, and therefore one gets the relation dP by dr is equal to minus gm rho by r square. This is the pressure gradient which is required to balance the gravitational force. And this equation is known as the hydrostatic equilibrium equation. Using this equation, we now try to see whether it is possible to estimate a limit to the central pressure. For this, again we consider the spherical system of radius r, which we take to be that of the star. We consider a shell of mass dm, and the mass of this shell is given by the volume of the shell multiplied with the mass density. This gives us the relation dm by dr is equal to 4 pi r square rho. This is known as the mass continuity equation or the mass conservation equation under the assumption that there is no mass loss from the system and the system is in equilibrium. We now write the hydrostatic equilibrium condition in terms of the independent variable mass. This when the mass is the independent quantity, then the equations are in Lagrangian coordinates. So, we get dP by dm is equal to dP by dr times dr by dm. If we substitute dr by dm from the mass continuity equation, we get the hydrostatic equilibrium in Lagrangian coordinates as minus gm by 4 pi r power 4. We now integrate this equation from the center to the surface of the star. Let us first look at the left hand side of the equation. This left hand side of the equation gives us the pressure at the surface minus the pressure at the center. The pressure at the surface is equal to 0 as this is an isolated system, and we are therefore left with only the pressure at the center. For the right hand side, we make a simplistic assumption because we do not know the relation of mass density as a function of r, or how the mass is changing as a function of r. While we know how m is changing, mr is changing as a function of dm, we do not know how r is changing as a function of m. We therefore apply a simplistic limit where we take r to be smaller than capital R, which is the size of the star. This gives us the relation GMR by 4 pi r power 4 is greater than GMR by 4 pi capital R power 4. Applying this inequality, we get the pressure at the center by this equation where the central pressure is greater than the integral 0 to m star Gm dm by 4 pi r power 4. Remember, mr is the same as the independent variable m. And once we solve for this simple equation, one gets the inequality where p of 0 is greater than gm square by 8 pi r power 4. Put in the value of m star and r for the sun, we get the central pressure to be greater than 4.4 10 power 13 pascals. From elaborate modeling, it has been found that the central pressure is of the order of 2.3 10 power 16 pascals, which is 3 orders of magnitude greater than the limit that has been obtained. Thus, we see that by a simplistic estimate, we can get a relatively good approximation to the limit of the lower limit of the central pressure. Is it also possible to calculate and get an idea of the average temperature of the sun? For this, we use a very important theorem which is known as the virial theorem. This theorem states that for an isolated gravitationally bound system in equilibrium, the average internal energy is minus half of the average gravitational potential energy. This theorem is a consequence of a hydrostatic equilibrium. There are numerous extensions and generalizations of this virial theorem that are possible relating the kinetic energy and the potential energy. The power of this theorem lies in the fact that it relates to scalar quantities. The relation of these two scalar quantities can be used to estimate important physical parameters of a system, which otherwise would be very difficult to calculate if one were to solve the equations of motions elaborately using Lagrangian or Hamiltonian. And consequently, there are numerous applications of virial theorem in astronomy. Here, we apply the virial theorem in order to get an average temperature of the sun. When formulated, this theorem becomes twice internal energy average plus the average of the potential energy given by omega is equal to 0. Now, for a sphere, the potential energy is given by 3 by 5 gm square by r. The internal energy is taken to be as the thermal energy of this entire system of particles within the star, and this is given by 3 by 2 mr average temperature by mu. Here r is the gas constant and m is the mass of the star. Mu represents the mean mass per particle in unit of proton mass. This can be taken to be 0.5 if we assume that the sun is composed of ionized hydrogen plasma. That is, the particles are electrons and protons. So, mu becomes roughly 0.5. Once we substitute the expressions of the internal energy and the gravitational potential energy into the virial theorem equation, one can get an expression for the average temperature of the system. And if we put in the values of the mass of the sun as well as the radius of the sun, one gets the average temperature to be around 2 million Kelvin. This temperature is lower than the central temperature, which is of the order of 15 million Kelvin. But it is a good estimate obtained by simplistic assumptions. In the main sequence phase, One can also derive various scaling relations between parameters. An important scaling relation is the mass-luminosity relation. This was first empirically observed in 1938 by Ham, who plotted the luminosity of the main sequence stars as a function of mass. Both these quantities can be observed directly. And it was found that the mass and luminosity have a very powerful correlation, and L is proportional to m power alpha. This power law index alpha was found to be of the order of 4 for low mass stars, that means between 0.5 and 2 solar masses, and was found to be of the order of 3.5 for the higher mass stars. Now, using this mass luminosity relation, one can also derive a mass age relation. We know that the age of the main sequence phase is given by the ratio of the nuclear energy to the luminosity. As the nuclear energy depends on the mass because of the mass energy relation, so E is proportional to m, and we know that L is proportional to m power alpha. Therefore, the age of the main sequence star is given by m power 1 minus alpha. We take the mass radius relation to be the radius is directly proportional to the mass. That is, larger the mass of the star, larger will be the radius. Using these relations, one can also derive the effective temperature mass relation using the Stephan-Boltzmann law, where the luminosity is equal to 4 pi r square sigma T power 4. Once we put in the scaling relations from above, we find that T effective is proportional to m power alpha minus 2 by 4. Now, these scaling relations are very useful in order to get a quick estimation of the stellar parameters of main sequence stars. Let us look at an example. For example, we take a 10 solar mass star. If we consider alpha to be of the order of 4, then its luminosity is given as 10,000 times the solar luminosity. Its age is inversely proportional to the cube of the mass. Since the age of the sun is 10 billion years, the age of a 10 solar mass star will be 10 million years. And the size of a 10 solar mass star will be 10 solar radii. The effective temperature of a 10 solar mass star will be given as the square root of 10 multiplied with the effective temperature of the sun, which can be taken to be of the order of 6000 Kelvin. This gives the effective temperature of the 10 solar mass star to be around 18,000 Kelvin. There is a lot of interest in trying to get empirical relations between these parameters, similar to what was discussed earlier. This plot shows the observed relation between the luminosity and mass of nearly 190 main sequence stars in binary systems, where the mass has been observed as a consequence of the binary motion. One sees that there is a strong correlation between the luminosity and the mass. However, a closer look shows that there is a spread in this mass luminosity relation, and therefore any model which tries to explain these mass luminosity relations should also be able to account for the spread in the mass luminosity relationship. This plot shows the radius mass relationship. One again sees that there is a strong correlation between the radius and the mass with a break at around 2 solar masses. For the stellar lifetime and mass, here what is shown in the plot are the results of 2 stellar models, and one can see again that the models also predict a strong correlation between the mass and the lifetime of the star. And finally, we see that this mass temperature relation of a number of main sequence stars shows that the two are correlated by a power law dependence, and there seems to be a break around log effective temperature around 3.6. Now, these observational scaling relations or empirical relations provide very useful constraints for the models of the stellar interiors of the main sequence phase, as well as for the evolution of the stars. Now, let us look at the energy generation of the stars in detail, that is the nucleosynthesis. So, nucleosynthesis represents the sequence of steps by which one element is converted to the other. In this nuclear process, the fractional mass is converted to energy, which is given by the mass energy relation E equal to mc squares. During the nuclear reactions, a number of conservation laws are applicable, and these are listed here. First is the conservation of electric charge, then is the conservation of nucleon numbers, that is the number of protons and neutrons. Then we have the conservation of lepton number. Lepton number is a quantum number related to the presence of leptons. Leptons are light particles such as electrons, positrons and neutrinos. This family also consists of other light particles such as muons and tauons, but for the nuclear processes that we will be looking at here, we will be considering only the electrons. The lepton number is +1 for particles and -1 for antiparticles. And finally, we have the conservation of energy and momentum. The nucleus of an element is represented by its atomic mass number, which is the number of protons and neutrons in the nucleus, as well as the atomic number, which is the number of protons. Let us look at how the conservation laws are applied for the most simplest nuclear fusion process, that is the fusion of two protons to a deuteron. If we look at the conservation of electric charge, on the left hand side there are two protons, so the charge is +2 on the left hand side. On the right hand side, one sees that there is a proton in the deuterium nucleus and a positron. So we have a charge of +2 even on the right hand side, so the charge is conserved. Now, if one looks at the number of nucleons, on the left hand side we have 2, and so do we on the right hand side. So therefore, the nucleon number is also conserved. Now, the lepton number on the left hand side is 0, as there are no leptons in the protons. On the right hand side, the deuterium nucleus has no leptons, but the lepton number of the positron is -1 and that of the neutrino is +1, and therefore the total lepton number on the right hand side balances out and is equal to 0. Thus, the lepton number is also conserved. The fusion of two protons occurs when they come close together, so that they are bound by the potential of the strong or nuclear force. For this, the two protons would need to cross the Coulomb barrier. This Coulomb barrier is proportional to the charge of the particles and inversely proportional to the distance between them. And if the particles are to cross the Coulomb barrier, then they should have sufficient energy, which can be provided by the thermal energy, and hence the relation E is equal to Z1 Z2 E square by 4 pi epsilon naught R, which is the Coulomb energy, and this is almost equal to the thermal energy. So, if one considers the case of the proton fusion, then one finds that for a distance of 1 Fermi, the temperature corresponds to 10 billion Kelvin. We know that in the case of Sun, the temperature is only 15 million Kelvin. Then how is it possible that nuclear reactions are occurring? This is because of the quantum mechanical effects, particularly quantum tunneling. And therefore, even at lower temperatures, there is a finite probability of the protons to cross the Coulomb barrier and undergo fusion to a deuterium nucleus. In general, one can calculate the reaction rates at any particular temperature. The nuclear reaction rates involve the nuclear reaction cross sections, which are obtained from laboratory experiments, the velocities of particles, which one can get from the temperature of the system, as well as the number densities of the particles. So, the nuclear reaction rate RIX is proportional to the number density of the particles, and one can see that it involves an integration over the energies. Now, the integrand in the integral is a combination of 3 terms. The first term is a slowly varying function of E, which relates to the cross section, and for small ranges of E, energy E, we assume this to be constant. The second term, which goes as the exponential of minus 1 by root T, relates to the tunneling probability, which increases with energy. The third term, E equal to minus E by kBT, relates to the Maxwell-Boltzmann distribution of particles. Here, generally in nuclear physics processes as well as in astronomy, one uses the notation for mass fractions in the form of x, y and z, where x represents the mass fraction of hydrogen with respect to the total mass, y corresponds to helium, and z is other heavier elements that could be present. Now, graphically one can see that for a particular temperature, the Maxwell-Boltzmann distribution is falling off, and the tunneling probability is increasing with energy, and therefore a product of these two gives rise to a function which is shown by the solid line here. This also corresponds to the integrand in the integral, and we see that this function has a maximum at a particular energy. This is known as the Gamow peak. Thus, for a given temperature, the reaction rate is maximum for a certain energy. Now, let us try to understand the fusion of hydrogen to helium in the core of main sequence stars. For this, we will look at the nucleosynthesis processes. So, the first reaction has already been discussed, where the fusion of two protons give rise to deuterium nucleus along with a positron and a neutrino. In the second step, the deuterium nucleus fuses with another proton to give a helium-3 nucleus, and energy is released in the form of gamma rays. Beyond this, there could be a number of pathways because the nuclear processes are probabilistic processes. One of the pathways is when two helium-3 nuclei combine to form a helium-4 nucleus with the release of two protons. Thus, in this process, 4 protons are used up in order to produce one helium-4 nucleus. This process or this set of pathways is known as the pp1 chain or the proton-proton 1 chain. The other pathway is the following, which happens 31% of the time. In this pathway, helium-3 nucleus interacts with a helium-4 nucleus to form beryllium-7. And beyond this, again there are two pathways possible. Beryllium-7 could interact with an electron to form lithium-7, which in turn interacts with a proton to form two helium-4 nuclei. This pathway is known as the pp2 pathway and occurs from the step above. This occurs 99.7% of the time. The other pathway from beryllium-7 involves interaction of this nucleus with a proton to give boron-8. This boron-8 decays to beryllium-8, which in turn decays to produce two helium-4 nuclei. This set of pathways is known as the pp3 chain. Thus, within the core of main sequence stars, the fusion to hydrogen and helium can happen through pp1, pp2 and pp3, although pp1 happens most of the times. The energy generation rate for the pp chain is given by this expression. Here x represents the mass fraction of hydrogen. There are various constants which take into account the complexities involved in the nuclear processes, and the temperature dependence of this energy generation rate is given by a complex function of the power law of temperature as well as an exponential power law of the temperature. As this is a complex function, it is usually the norm that very close to a certain temperature, a simple power law is fitted to the function. For the temperature close to 15 million Kelvin, which is the temperature in the core of the sun, it is found that the power law fit to the energy generation rate is given by the fourth power of temperature. Now, how do we know that this is the sequence of steps that is generating energy in the core of the sun? Is there some way to confirm this? This was confirmed with a very beautiful and elegant experiment to detect neutrinos from the sun. The neutrinos in the pp chain are produced in three reactions where the energy thresholds, that is the minimum energy of the neutrinos produced, are different. The first is in the pp1 chain which is in the proton-proton reaction. The second is in the pp2 chain when the neutrino is produced in the interaction of a beryllium with a nucleus with positron, and third is in the pp3 chain where a neutrino is produced due to the decay of boron. Neutrinos are in general very difficult to detect because they are neutral, very low mass, and they have very low interaction cross sections of the order of 10 power minus 46 meter square. Among the three reactions from which neutrinos could be detected, this experiment, the sensitivity of this experiment was such that it could only detect the neutrinos from the third, that is the boron decay process, because they had the highest energies. This experiment involved having a large volume, nearly 100,000 gallons of a liquid which was tetrachloroethylene. The idea behind having such a large volume is because of the very low interaction cross section of the neutrinos. And this experiment was designed by Raymond Davis and his colleagues at the Brookhaven National Laboratory, and the reaction which was used for the detection was the interaction of the neutrino with 37 chlorine, which gives 37 argon. Now 37 argon is radioactive and it decays to other products which can be detected using normal particle detectors. As the interaction cross section of neutrinos is small, a very small number of argon nuclei were produced over several days which were collected. As this is a very sensitive experiment, precautions were taken in order to eliminate the effects of stray neutrinos. And through this beautiful experiment, neutrinos were detected from the sun. However, along the path, other discoveries were also made, such as the neutrino mass as well as the oscillation of the three neutrino flavors. This picture shows the experiment by R. Davis at the Brookhaven National Laboratory, and for this experiment, Raymond Davis received a Nobel Prize in 2002 in physics. Now, are there other pathways by which protons can be converted to a helium nucleus? And it so happens that at higher temperatures and pressures, there are other pathways possible. For example, at a few tens of millions of Kelvin, that is 20-30 million Kelvin, the other pathways include using carbon, nitrogen and oxygen nuclei as catalysts in the production of helium nucleus from protons. So, few of these pathways are shown here. Here, for example, as one can see, the carbon-12 nucleus interacts with a proton to produce nitrogen-13, which decays to carbon-13. This carbon-13 interacts with another proton to produce nitrogen-14, which again interacts with another proton to produce oxygen-15. This oxygen-15 being unstable decays to nitrogen-15, which interacts with another proton to produce back carbon-12 and a helium nucleus. Thus, in the process, carbon is produced back again and 4 protons are used up to produce helium nucleus. There are other such pathways that are possible, and these pathways are categorized as the CNO cycle. Thus, in the CNO cycle, the protons are converted to helium nucleus using trace amounts of carbon, nitrogen, oxygen that may be available in the course of the stars as catalysts. The energy generation rate for this reaction is given by the expression shown here, and here the X corresponds to the mass fraction of proton and XCNO corresponds to the mass fraction of carbon, nitrogen and oxygen combined. Again, we see that the power law, that the energy generation rate is a combination of a power law of temperature and exponential power law of the temperature. And if one were to again Consider a power law match, a simple power law fit to the energy generation rate as a function of temperature. Then near 20 million Kelvin, one finds that this is of the order of 20th power of the temperature. Thus, a small change in temperature can lead to a very large change in the energy generation rate. The CNO cycle for the production of helium from protons is the primary source of energy in stars whose mass is greater than 1.5 to 2 solar masses, as the temperature and pressure conditions achieved here are larger. With this, we come to the end of this lecture. Thank you.